All right, let's talk about one of the most famous, most fundamental problems in all of programming, two-sum. Now, you might have heard of it, you might have even solved it, but today we're not just looking for an answer. We're going to treat this problem as a gateway, really, a way to unlock a much more powerful way of thinking, and we're going to do it together.
And this quote really hits the nail on the head. This is the whole point of what we're doing today. This isn't just about getting the right answer and moving on. It's about a fundamental shift in how we think about problems. We're going to see how just one clever little data structure can totally transform our entire approach.
Okay, so here's the quest. Here's the challenge laid out for us. We've got a list of numbers, 2, 7, 11, 15, and we have a target number, 9. All we have to do is find which two numbers in that list add up exactly to 9. And not just the numbers, but their positions, their indices. Seems simple enough, right? So let's think about how we might tackle this first. All right, section 1, the first attempt. And where do most of us start? With brute force. Just trying everything until something sticks.
And this way of thinking is completely natural. It's probably the first thing that pops into your head. You just think, okay, let me try every single combination and see what works. You'd grab the first number, 2, and you'd pair it with everything else. Does 2 plus 7 equal 9? Yep. But what if it didn't? You'd check 2 plus 11, 2 plus 15, then you'd move on to 7 and do the same thing. It's thorough, for sure, but man, as we're about to see, it is not very smart.
And here's what that mental model looks like when we turn it into Python code. Check this out. It's pretty straightforward. You've got two loops, one right inside the other. So that outer loop grabs a number. Let's say it picks up the 2. Then the inner loop kicks in and goes through the entire list all over again, pairing that 2 with every single other number. And that little if statement right there, that's our check. Does the sum equal the target? It literally, painstakingly checks every single possible pair.
So you can probably already see why this isn't ideal. I mean, it's doing a ton of extra work, right? It's clumsy. It even checks numbers against themselves. But the biggest, ugliest problem here, the thing that makes this a terrible solution for any big list, is just how inefficient it is. And that brings us to the villain of our story. It's time complexity, or what we call big O of n squared.
So what in the world does O of n squared even mean? Well, think of it like this. If our list has, say, 10 numbers, our code has to do about 100 checks. Not so bad. But what if the list has 1,000 numbers? Suddenly, we're doing 1,000,000 checks. And if it has 1,000,000 numbers, well, you get the picture. The amount of work absolutely explodes as the list gets bigger. This is a performance nightmare. This is the villain we need to defeat. And just in time, our hero arrives. Let's talk about the breakthrough, thinking with hash maps. This is where everything changes. This is the moment we stop just grinding through every possibility and start being, well, clever about it. Let's see how this completely flips the problem on its head. And really, it all comes down to this one simple question. What if we could stop doing all that repetitive work and just remember what we've seen? Instead of scanning the list again and again, what if we just looked at each number once and kept a little note of it? What if we could just ask a simple question like, hey, have I already seen the partner I'm looking for? And that question leads us to a totally new mental model. It's a simple but honestly a profound shift in thinking. Instead of check everything, our new motto is check first, then store. For every single number we look at, we first peek into our memory to see if its partner is waiting for us. If it's not there, no problem. We just jot down the current number in our memory so a future number can find it.
And this is the beautiful code that brings that new model to life. The first thing you should notice, the 2 loops are gone. We're down to just 1. We start by creating this empty dictionary, which we're calling prevmap. Just think of this as our brain or our cheat sheet. It's where we're going to store the numbers we've seen and where we saw them. Then we just loop through the list one time. For each number, we figure out what its partner would be. We call that the complement. And here's the magic, the most important line. If complement in prevmap, that's us asking our cheat sheet, hey, have we seen this number before? And that check is practically instantaneous. If the answer is yes, boom, we're done. If not, we just add the current number to the cheat sheet and keep going. It's so simple.
Okay, let's walk through this step by step just to see how fast it is. First, we're looking at the number 2. We need to find its partner to get to 9, right? So, 9 minus 2 is 7. We look in our memory map. Is 7 in there? Nope, it's empty right now. So, we just add 2 and its position, index 0, to our memory. Cool. Moving on. Next up is the number 7. What's its partner? 9 minus 7 is 2. We check our memory map again. Is 2 in there? Yes, it is. Boom, we're done. We found our pair in just 2 steps. That is incredible.
I mean, look at this comparison. It says it all. We went from the brute force check everything mindset to this elegant remember and jump strategy. And the result? The complexity just plummets. We go from that scaling nightmare, O of n squared, to a beautiful lightning-fast O of n. What that really means is, if our list gets 10 times bigger, the work we have to do only gets 10 times bigger, not 100 times bigger. That is a game changer. It's a massive, massive win.
So you might be thinking, okay, that's a neat trick for one little problem, but why does two-sum matter so much? Why does every programmer learn it? Because the lessons here are absolutely huge, and they apply to so much more than just this one challenge.
You'll often hear programmers call two-sum a canonical hashing problem. That's just a fancy way of saying it is the perfect, classic example of a concept. It's like the textbook case. If you can really wrap your head around how hashing crushes this one problem, then you've basically unlocked the core logic for using hash maps to solve an entire category of other problems. It's the key.
And this table really lays out what two-sum teaches us about hashing. First, it forces you to see exactly why brute force is so bad. Those double loops are just too slow. Then it shows you the incredible power of an instant lookup. That if x in map is like magic. It introduces this powerful complement idea, where you calculate the thing you're looking for. And maybe most importantly, it teaches you one of the most fundamental trade-offs in computer science, using a little bit of extra memory to save a ton of time.
And believe me, this is not just some one-off trick you'll use once and forget. This pattern of using a hash map to remember what you've seen before is a cornerstone of algorithmic problem solving. You're going to see this exact same logic pop up again in tougher problems like three-sum. Anytime you need to count how many times something appears. In subway problems, the list goes on and on. It's a tool you absolutely need in your toolkit.
So at the end of the day, the real takeaway here isn't a snippet of Python code. It's a new way to think. It's a new tool for your brain. The next time you're staring down a problem, and your first instinct is to check everything against everything else, just stop, take a breath, and ask yourself this question. Where can I remember and jump, instead of just checking everything? How can I use a little bit of memory to save myself a whole lot of work? Because that shift in thinking, that's the real solution. That's the real win.